All right, so last time we ended with, we looked at all the composite functions and we saw all the different ways we could calculate them. And so one of the applications of combining functions and using composite functions is the difference quotient. And like I said, this is a really important idea, and it comes from the average rate of change formula, which you guys know is the slope formula. So this is, once again, just calculating slope in a slightly different form. This is your change in y, right? This is your change in x. And we said that the slope of this line right here between these 2 points, right, if we let the delta x get smaller, so if I take this point, right, and I slide it down closer and closer and closer, first we'll see that the slope of that line will change. It'll start to increase. And then if we get to a point where those 2 points are basically lying on top of each other, what you'll end up getting is the tangent line at that location. So that's what the difference quotient does. The difference quotient is just a variation on the average rate of change formula, where instead of saying b minus a, we call that whole distance x. So if you look at the x-axis here, right, instead of a, we're going to have some value x at that point, right? We're saying the distance between a and b is h. So this value b, right, is actually x plus h on the x-axis. So remember, when you're reading a number on the x-axis, it's the distance back to 0. So x is the distance all the way back to 0, and then this distance x plus this value h is where b is located. So that's what this difference quotient is giving you. It's giving you the change in y, now in a new notation, over the change in x, which is h. So we ask you in pre-calc to set up difference quotients and simplify. When you get into calculus, you'll actually take the problem one step further, and you'll actually learn what limits are, and you'll actually apply a limit to your final result. But in calculus, the biggest issue is doing the algebra of the difference quotient. So that's just an algebra problem, and it kind of fits in with the section we're working on now. So I want to do a couple of them and show you some just kind of crazy algebra moves that can come up that if you haven't seen in a while can definitely trip you up. So if we want to look if we want to set up the difference quotient, right? Let's do something easy at first, right? For the function x squared. One thing that you can do to kind of make the math easier so you're not writing like this giant fraction after fraction after fraction is we can actually set this up in parts and then build the difference quotient. So the first thing I want to do in the numerator is I want to figure out what f of x plus h is. So f of x plus h, all this says is take my function f of x and everywhere I saw an x, now replace it with an x plus h. So that means this is x plus h squared. I'm just plugging it into f of x. Then I want to go ahead and expand it out. I'd rather do the algebra up front before I build the quotient. So when we FOIL this out, we're going to get x squared plus 2xh plus h squared. So that's just expanding that guy out. F of x is just going to be the original function, right? And h is h. So let's build our difference quotient. So f of x plus h, right, we said was x squared plus 2xh plus h squared. And then we're subtracting f of x, which was just x squared. And all of that goes over h. So we're not just going to ask you to build this guy. It's implied in the question that when we ask you to build the difference quotient, you have to simplify it completely, okay? So if we look at this numerator, right, I can see that I have a positive x squared right here and a negative x squared right here. So those are actually going to cancel each other out. Now, this particular equation, the difference quotient, what should always happen is in the numerator, you should end up being able to cancel out all the terms without h's. You should always end up with everything with an h in the numerator, and then the goal is to cancel the h in the denominator. That's what's going to happen, because you'll see when you get into calculus, that's what has to happen, because we're going to ask you to plug in h for 0 in calculus, and you can't have 0 in the denominator. So the whole name of the game of this quotient is to make sure the algebra is flowing in a way that you can cancel the h in the denominator. So that's a good tell when you're doing the problem. If you can't cancel all the terms without an h in the numerator, you probably need to do more algebra, or you've made an algebra mistake. So x squared canceled x squared, so now all I'm left with up top, right, is 2xh plus h squared over h. Well, you can see every single term in the numerator has an h in it. So that means I can cancel an h out of the top and cancel the h out of the bottom. So when you're canceling, it has to come out of every single term, right? Another way you could do this is you could say, well, I'll factor the h out front and then cancel it. But we can say, well, one h goes away, right? One h goes away, and that h goes away. So since I had an h squared, I still have one h left on that last term. So now the result is 2x plus h. So like I said, if we were in calculus, we would actually have one more step after this, and what we would do is we would plug in zeros for all the h's, and we would get our final answer as 2x. But for this class, you would leave the h's there because we don't really know why we're plugging in 0 yet. But if you go back to the geometry of what we looked at, plugging in 0 for h makes sense, because the goal here is to make this 0 so that we're getting the tangent line slope out of the equation rather than the secant line slope out of the equation. So this is a pretty straightforward basic one with polynomials. The big issue is expanding them out. So if I gave you x cubed, the biggest issue in the problem would be cubing x plus h out, right? So let's look at some other kind of nutty moves we can make, and this is where people kind of get into trouble because they don't remember their algebra. All right, let's set up the difference quotient. I'm just going to show up, yeah, for f of x equals 1 over x. Here, I'll get a darker color. So if we look at this, right, well, f of x plus h, we simply plug in, right, x plus h everywhere we have an x. So if we set up the difference quotient, right, it says, well, 1 over x plus h minus f of x, right, which is 1 over x, all over h. So to simplify this guy, right, we're going to have to get a common denominator in the numerator. Now there's another sort of way you can do this when you're dealing with fractions, so you're not having to write this big giant fraction, because sometimes you can get into the weeds and you forget which is the numerator, which is the denominator. Well, one thing you can think of, that h in the denominator is really h over 1. So when you multiply, or excuse me, when you divide a fraction by a fraction, right, we multiply times the reciprocal. So another way I could write this out to make my life a little easier is I could say, well, that's 1 over h times, right, x plus 1 over x plus h minus 1 over x. So now I'm just writing it in 2 lines. I'm not having to write it as a big giant fraction. Does anybody not see what I did there? Right? So that h in the denominator, whenever you have a whole number in the denominator, it's really itself over 1. And you can treat it like a fraction and multiply times the reciprocal. All right, so if we want to get a common denominator to combine those two fractions, right? Well, the common denominator is just going to be the product of the two numbers because there's no common terms there. So that means I have to multiply this by x over x, and I have to multiply this by x plus h over x plus h. So I'm actually going to write that out so you guys can see what I'm doing. So I'm going to take 1 over x plus h. Oops, get another color here. And I'm going to multiply this first guy by x over x, right? Then I'm going to take minus 1 over x, and I'm going to multiply it by x plus h, right, over x plus h. Right, so that's what we said when we're getting the common denominator. So all I'm doing is multiplying each one of those fractions by the number 1, right? And 1 just is going to change its appearance, but it's not going to change its value. Okay, so then once we do that, right, we're going to we still have our 1 over h out front. This first term, right, is going to be x over x times x plus h, right, minus x plus h over x times x plus h. And you don't have to do this in as many steps as I'm doing it. You can actually kind of go from the first line down to the next line if you see it, but I'm just writing all this out because for some of you it's probably been a while since you've done this. But now that I have a common denominator, right, I'm allowed to just combine the numerators. So, right, if you have 2/3 plus 1/3, you can just add 2 plus 1, right? So what I'm going to get here is x minus h, because this negative sign gets distributed across that numerator. Right? And then this is still over x times x plus h. So look what's going to happen here. All the terms in the numerator without an h are going to go away again. So this h, or this x, right, cancels this x, and all I'm left with is negative h over x times x plus h, right, all times 1 over h. So just like in the last problem, we can cancel the h out of the denominator. So this would be the result of the difference quotient, and if we did the next step of plugging in 0 for h, you would see we would get 1 over x squared, or negative 1 over x squared, right? So some of you may have seen a little bit of calculus in high school, and some of you may have heard the word derivative, right? And that's what this equation does, is it's giving you the derivative of the original function, and that's what you'll be doing a lot in Calc 1. But notice the pattern of what happened. The terms without an h in the numerator went away, and we were always able to cancel the h out of the denominator. All right, so working with fractions can be really tricky, and you want to make sure that you're, like I said, distributing the negative sign across when you have the numerator. All right, so let's look at how to deal with radicals. So let's do this for the square root of x. So we plug in x plus h, right? We'll just get the square root of x plus h. So if we build our difference quotient, we're going to have the square root of x plus h minus the square root of x all over h. And just like with the previous two examples, everything without an h in the numerator should cancel. What you absolutely cannot do is say that the numerator just equals the square root of h. You cannot do that, right? You can't add and subtract things inside the radicals. You have to do another step in order to get that done. So the only way we can get that x plus h out of that radical is we have to somehow figure out a way to square that radical. It's the only way to make a radical or square root disappear, right? So there is a tool that we use in algebra to do that, and we call it the conjugate, right? So when we multiply times the conjugate, what you do is you take the exact same expression and you flip the sign. So this is a subtraction, so we would multiply times the sum of those two things. But algebraically, what you're really doing is you're creating a difference of squares. So if you have a minus b and you multiply it by a plus b, what you get, right, is a squared minus b squared. Similarly, if you see a squared minus b squared, it will always factor into a plus b, a minus b, and we call that the difference of squares. And so if you FOIL that out, you'll see the a squared, right? Then you'll get a positive ab, then you get a negative ab, so the middle term always cancels when you have a difference of squares, okay? So that's what the conjugate's going to do. It's going to create a difference of squares. So I'm going to multiply the numerator by the conjugate, which is just x plus h plus the square root of x. And whatever I do to the numerator, I have to do to the denominator. So once again, I'm just multiplying this guy by 1. So that's why it's a legal move. If there had been a plus sign in the original problem, then the conjugate would have had a minus sign. So it's always the opposite sign, and it's going to create a difference of squares. So what we have here is a minus b, right, times a plus b. So there's no need to FOIL this guy out. We actually know it's going to multiply out to be a squared minus b squared. So when I multiply the numerator, I'm going to get the first term squared, which is just x plus h, minus the second term squared, which is just x. In the denominator, we have h times the square root of x plus h minus the square root of x. So it's just this guy times this guy, and up here, we got a difference of squares. Does anybody not see how that worked? I can't tell if you guys are just, if it's early or what. All right, so x minus x in the numerator, once again, all the non-h terms went away, and you're left with h over h times the square root of x plus h, right? Oh, this should be a plus. Nobody caught that. All right. Sorry, when it was a plus, I forgot to write as a plus down here. So now the h's cancel, just like they should. So the h in the numerator cancels the h in the denominator, and our final answer is 1 over the square root of x plus h plus the square root of x. Yep.
This is like back to the beginning of the problem.
Mm-hmm.
Why is the h in the f of x square root?
Because the functions that evaluate f of x plus h and whatever's in those parentheses, you go to the original equation and you replace x with that thing.
But why would it not just be like square root of x?
Because the x lived under the radical, so anything I replace x with has to be under the radical. Yeah. Mm-hmm. If it had been like we did a problem Friday where, let's see if I can find it, when we were composing our functions, and right, when we plugged x plus 5 into the square root of x, you see it all lived under the radical. But when I plugged the square root of x into here,
Okay.
then the 5 stayed outside. Yeah. Mm-hmm. So you just have to be really, really careful when you're setting it up. So these are 3 of the most common moves. We'll have you expand some kind of polynomial term. We'll have you do a problem with a fraction, so you have to find common denominators and know how to cancel that stuff. Or we might give you something with a radical, and you have to understand how to use the conjugate. So those are the 3 kind of biggest moves that kind of trip people up when they're doing these problems. So they just take a little bit of practice, and I think there's a section in Alex on your homework in 1.8. I think there's a topic on like calculating out the difference quotient. But you should see the non-h terms go away, and you should always be able to cancel that h out of the denominator. That's how you know you're done. When that h is gone out of the denominator, that's usually when we say we're finished with the problem in here. All right, any questions about that? Okay. All right, so what I want to do is I want to switch gears for a second, and I want to go back and take a look at some more domain and range problems with dealing with composite functions. And I want to look at the problem we had in the homework set first, where we had multiple domain restrictions, and showing you guys how to deal with that. So I just want to get this problem copied right. But it was number 6 on the homework, and it threw some people for a loop. Yeah, here we go. Okay, so the function was this. And we wanted to find the domain of this guy. So remember we said we had 3 rules, or 3 things we needed to check for, right? We can't have negatives under radicals. we can't have zeros in denominators, and we can only have positive things in logs. So there's no logs here, so we're good with that. The x to the fifth term out front is fine. It will accept all values of x, so we don't have to check that. But we do have a radical, and we do have a denominator, and we have to deal with that. So you look at them separately first, right? So the radical says, because it's in the numerator, well, the entire expression under the radical cannot be negative, but it is allowed to be 0, because 0 in a numerator is okay. So we would say, well, negative x plus 3, you just copy the expression. This has to be greater than or equal to 0. So we're saying no negatives, right? Then we solve this for x. So I'm just going to add x to both sides. So x, right, is less than or equal to 3. So I think I mentioned this earlier in the class, but just to reiterate, it made sense the way the expression was written for me to move x to the other side. But for some reason, when students see inequalities, you guys always want to read them left to right. And that's okay, but if you read it left to right, it says 3 is greater than or equal to x. When you're doing domain problems, it makes way more sense to read the inequality from the x position. So you can also read an inequality from right to left. So I usually go to the x, and it says, oh, x is less than or equal to 3. That gives me a better understanding of what's really going on here, rather than 3 is greater than or equal to x, because I'm looking for the x values. So any value less than or equal to 3 is fine, but now we have to deal with the denominator. So the denominator, right, the entire expression in the denominator is not allowed to equal 0. So there are two ways algebraically you could solve this problem, right? You could see a difference of squares, because that's what you have, x squared minus 1, 1's a square. And you could say, well, I'm going to factor this, right, to a plus b, a minus b, and then from there, you can see, right, that x isn't allowed to be negative 1 or 1. The other way you could have done this problem, and it would have been perfectly fine, is you could have added 1 to both sides and said x squared cannot equal 1, and then from there taken the square root of both sides, right, and said, well, x can't be plus or minus 1. So both paths would get you there. So what we're saying now, and remember, when we're looking at domain, the minute we've determined an x value is not okay, it's kicked out of the domain. It doesn't matter if the numerator will accept it and the denominator won't, or vice versa. Once it's out for the whole problem. So if we want to actually write out what the domain of this is, we have to account for both restrictions. So I'm going to draw a number line here. I think it's a little easier if you visualize it. And I'm going to label negative 1, 1, and 3. So the denominator says negative 1 and 1 are not okay. So I'm going to kick them out of the domain by using an open circle. So that's just going by the denominator, right? The numerator says, and this is where it makes more sense to read it right to left in this case, the numerator says x is less than or equal to 3. So if it's allowed to equal 3, right, we keep it with a closed circle. If x is less than or equal to 3, then I shade everything to the left, because I can't say that, less than is left. So I shade all the values to the left, but notice I'm not including negative 1 or 1, because the denominator kicked those out. So if you only check the numerator, you probably would have shaded all of this part of the number line, right? But then the denominator kicked those extra 2 values out, so you had to exclude it. So if we write this in interval notation, right, we just read the number line from left to right. So we would get negative infinity to negative 1 not included. Then it picks back up at negative 1 and goes to 1. Neither of those are included. And then it doesn't allow for 1, but it does accept 3. So it would be 1 to 3 included. So when we use these rules in combination, you just want to be careful that you're accounting for every possible combination that you could see, and you're reconciling those two things together.
Can
Can you repeat like
Mhm.
the 3 rules that you have to check for in the beginning?
Yeah, so it's no zeros in the denominator. No negatives under even roots. And then the third one is only positive values inside logs, but we won't talk about logs till second unit.
Thank you.
Yeah. So remember, if the numerator, if the radical is in the numerator, 0 is okay. If the radical is in the denominator, then you have to kick 0 out because you have 2 rules being combined there. Yeah. Okay, so I wanted to look at another example that I had. Oh, I take that back. I want to talk about that line problem on that homework set. A lot of people had trouble with that. The guy with the 2 jobs. Yeah. I want to talk about that. Because once you see it demystified. All right, so the issue with that problem, right, was we had a guy, his name was John, right? He had 2 jobs. And the first job, he was going to work 5 days a week, 8 hours a day, right, Monday through Friday. Then his second job was a weekend job, and he was going to work 2 days a week, Saturday and Sunday, for 5 hours a day, and he had 2 different pay rates. And so what they wanted you to do, and this was the issue, was they wanted you to write a linear equation, right, for the amount of money he has earned in a given week since starting his new jobs. So, but the trick here was you had to know that the input variable was going to be weeks. So you put in week 1, week 2, week 3. But the units you were given the information in the problem were in hours, days. So all we had to do here, so this was number 11 on that worksheet, right? So let's look at job number 1, okay? So job number 1, it said, well, he's going to work 5 days a week, right, times 8 hours a day, and he was going to be paid $15 per hour for that first job. So if you look at this, and any one of you that's taking chemistry, I'm going to do a little dimensional analysis, you can see here that days cancel days, right, hours cancel hours, and this works out to be $600 per week. So now what you have is the rate of money per week that he's making. And that's what the line has to be defined in, is in weeks, right? At job number 2, he works 2 days a week at 5 hours per day, and he's paid $13 an hour. So once again, days cancel, hours cancel, and now you're getting $130 a week. So these are the slopes, right? If we wanted to look at each job separately, then $600 would be the slope of job 1, $130 would be the slope of job 2, because that's the rate for the week, right? But the total amount he makes every week on a typical week is $730. So this is going to be the slope of our function because we want to measure how much money he makes every week. But then they added this extra little fun tidbit, right? Because to do a line, we need the slope and a point. So we need some data point to give us the point to plug in. But they said in the problem, well, the first week he starts his job, he only works at job number 1 for 3 days. So we actually can calculate, right, that if he works 3 days, right, for 8 hours a day, and we know that job number 1 pays him $15 an hour, that very first week, he makes $360. So our data point is that on week 1, he makes $360. But then after that, he's gonna make $730 a week. And so if you look at the units, right, dollars is all that comes out there. So once you have your point and your slope,
Why would it
Mhm.
be in the Y, not the X, value? Like, why would it?
why is the money the Y?
Yeah.
Because weeks go in, right? That's what the function they want us to build says, we want to write a function for the amount of money earned in a given week. So meaning you're going to put the week number in and the money comes out. So you can imagine this, like if you ever get a paycheck and you see the year-to-date column, right? It tells you how much money you've made year-to-date. That's what this function is going to do. It's going to tell you how much money you've made since starting the job for any particular week of the year, right? So we can kind of imagine that this is the beginning of the year, you start a new job, and that's your year-to-date amount. So that's a good question because you have to know what's your input, what's your Y. The other way I knew to do it that way was look at the slope. Look at the units of the slope, dollars per week. That means that's Y, that's X, because slope's delta Y over delta X, okay? So now if we use the point slope formula, we say, well, Y minus 360 equals 730 times X minus 1. I'm going to distribute the 730 and then add 360 to both sides. Which, be careful about transposing numbers here because it is 730 and then it's 370 is what the intercept worked out to be. And so if you plug in numbers, if you plug in 1, you'll see that the first week he made 360 and then every subsequent week he makes an additional 730. So it actually accounted for the data points that we needed. And this one you could have, it really wouldn't have been a good way to do it, but like if you had put 0 360, like called those 3 days week 0 and then just started counting the full weeks, that's technically not right, but I understand why somebody would do that. But because a lot of times we start at time 0, but in this case it was kind of the way the problem was worded and the way they wanted the line, you wouldn't have been getting the right answers. You would have been off by a little bit. So you really needed to call that first week 1 to make this make any sense. So is that, so one of the things you want to make sure when you're doing these applied problems is look at the units of the problem. But once you see it kind of worked out, it actually wasn't that bad of a problem at all. It was very easy once you figured out how to get the slope and the data point. Yeah. Okay. All right. Well, does anybody have anything else they want to talk about? Kind of some free time. You guys are running a little ahead of my other sections, so.
Is Alex due tonight?
I think there's an Alex deadline tonight, yeah. And we're running like a day ahead on the schedule, which is good because that means we're gonna have more time to prep for the test. And this Thursday night at 6 o'clock, which I'll send out an email. It's gonna feel really early because we moved the test date back, but that's gonna be the first exam review. So if you can't come to the live review, they go about 2.5 hours. They're pretty long, but we could do a lot of test level questions. If you can't come to the live review, it's fine. It'll be recorded and you can watch the playback if you need to watch the playback. And then we'll have our in-class review day the day before the test, yeah.